Hello, this is the walkthrough for the fall 2017 final for MA261. Okay, question one. A line L contains this point and is parallel to this line. And we want the point on L where we intersect the plane y equals 0. So we know if we want a line parallel to another line, we have to have the same coefficients for t in both lines. So the form of a general line that is parallel to this line will be x equals 3t plus c, y equals negative t plus c, and z equals negative, 3t plus c. And really these are different c's. These can be whatever constants we want. In the case of this line, it's 5, 1, 1, but they're telling us that our line contains the point 1, 4, negative 3. So for t is equal to 0, we want x to be 1, y to be 4, and z to be negative 3. And so here is the parametrization of our new line. Now we want to intersect the plane y equals 0, and in order to figure out what all of our points are, we know that it's going to be something in the form something 0 and then something else, but we don't know what t value this exists for. So if y is equal to 0, 0 equals negative t plus 4, we see that negative 4 is equal to negative t, and so t is equal to 4. So if 4t is equal to 4, we can solve for the rest of these guys. 3 times 4 plus 1, that's going to give us 13. And 3 times 4 minus 3 is going to give us 9. And there's our answer. Okay, the plane passing through this point, parallel to this plane, intersects the x-axis at what point? Well, we know that just like if we want to have two lines that are parallel to each other, they must have the same t coefficients. If we want two planes to be parallel to each other, they must have the same normal vector. So in the case of this plane, our normal vector is 1, 1, 2. And so we know that our other plane will be in the form of x plus y plus 2z equals some constant. And we can find that constant by plugging in the point that we know that the plane passes through, which is 0, 1, negative 1. So that will be 0 plus 1 minus 2 is negative 1. So negative 1 is our constant over here. And now we need to see what happens with, or what our point on this plane that intersects the x-axis is. Well, we intersect the x-axis in 3D space when y and z are both equal to 0. And so x plus 0 is negative 1. So our point will be negative 1, 0, 0. The position of a particle is given by this r of t when t is equal to 0. After the particle has gone a distance of 3, the x-coordinate is what? So we know that we can find this by integrating from 0 to whatever value of t will have us go a distance of 3. So let's call that a. We don't know what it is. That's what we're solving for. And then we're going to need the square root of the sum of the squares of the derivative of r of t. And it's a lot less complicated than it sounds because r prime of t is just going to be 2, negative 2, 1, which when we set up our square root with 2 squared plus negative 2 squared plus 1 squared, that's just going to be 9. And so this simplifies down to 3 dt. And so solving, we are essentially solving the equation 3t 3t on 0 to a. So 3a minus 0 equals 3 because we need this. Should have put that earlier. We need this whole thing to be equal to 3 because we need to find the coordinate where we have gone a distance of 3. So we see that we can solve this and see that a equals 1. And this makes some sense because our integral from 0 to 1 of 3 dt, we don't have any t's in here, we're just going to multiply by 1. But careful, because that is not our answer. That is just the t value for which we have traveled a distance of 3. We have to find our x-coordinate, and we know that the position of our x-coordinate is defined by 2t, and t is equal to 1 in this case, so our answer is 2. Okay, the tangent plane to this level surface at this point is given by this equation. So we know that our tangent plane is going to be given by, in this case, okay, let's be clear. Let's call this entire function, I don't know, g. Why not? This is g of x, y, z. We know that our tangent plane is going to be g, start with x, gx, x minus x naught, plus gy, y minus y naught, plus gz, z minus z naught. And so we can solve for all of these, and we should have our tangent plane. So let's find gx. That's going to be the partial derivative of this guy with respect to x. That will give us 2x plus 4y. Gy is going to give us 4x, and gz is going to give us 4z cubed. So now we know that we're at the point 2, negative 2, 1, so we can plug those values in and solve for gx, gy, and gz. So this will be 4 minus 8, so negative 4. This guy will be 8, and over here we get 4. So we can set this up because we know our x naught, y naught, and z naught. X naught, y naught, z naught, those are just going to be these values up here. So x naught is 2, y naught is negative 2, z naught is 1. So at this point, we should be able to set everything up with our equation and get a real answer. So gx is going to be negative 4x minus x naught, which is minus 2, plus 8, which is gy, y minus negative 2, so plus 2, and then gz, which is going to be plus 4, z minus 1. So let's solve this. Right off the bat, we can divide everything by 4. That'll make our lives easier. This will be 2, this will be 1. So we will get negative x plus 2, negative x plus 2 plus 2y plus 4 plus z minus 1. And that is all equal to 0, and so we can move things over, and we will get negative x plus 2y plus z equals, well, this is going to be 5 on this side, so it'll be negative 5 when we move it over. And we see that if we take everything here and multiply it by negative 1, which is just the same thing as switching everything to the other side, we have answer choice C. Okay, let's consider this function. Which of the statements are true? The function is continuous at 0, 0. Okay, so really this is a limits question in disguise, and we'll see why in a sec, because in order to prove that the function is not continuous at 0, 0, we need to prove through the two-path test that the limit as x approaches, as x and y approach 0 of xy over x squared plus y squared, we need to prove that this does not exist. And we can do that through the two-path test. So if we approach along the line, we approach 0, 0 along the line x equals 0, then this is going to work out to 0, yes, 0 over 0, which is still pretty bad. So this will be in the form 0 over 0. But if we approach on the line y equals x, setting every y we see equal to an x, we will get x squared over x squared plus x squared, which will simplify down to 1/2. And by the two-path test, since we found two different limits, two different limits on two different paths, we know that this limit does not exist. So the function is not continuous at 0, 0 because, if we have a 0, 0 point, this is a simplification in two dimensions, but we're equal to 0 at 0, 0, but around 0, 0, approaching it, we're not necessarily approaching it in the same way, and we're definitely not approaching 0. Okay, the partial derivative of f with respect to x, so, sorry, well, let's conclude. This is not true. So anything with 1 in it is false, and also all of the above is false. So partial f partial x at 0, 0 is equal to 0. So this isn't something that I can go into depth about the proof and why a partial derivative is what a partial derivative is. I just simply do not know. But I do know that all this is really saying, the only condition that we need for this partial derivative to be 0 is for it to be defined at 0, 0, which it is, and the partial derivative of 0 with respect to x is definitely 0. So this is true. And then we see that outside of 0, 0, this function here doesn't really have anything wrong with it. Our only asymptote will be at 0, 0 because there are no positive or negative values when squared and added together that equals 0, which would make our function do all kinds of crappy stuff that we don't like and would make it not differentiable. But we're pretty differentiable everywhere else, and so this is also true. So 2 and 3 is our answer. Okay, let's suppose that f of x and y is the function g of x multiplied by the function h of y, where h and g are continuous differentiable functions of one variable, and then they give us a bunch of info about them. And we're meant to approximate f of 1.1, comma 2.2. So we can do this using differentials. We know that, let's see, that our, I'm not sure really how to notate this, but we can express the total, the approximate change in g. So I'll call this g with a little delta because we're going to use delta g in a sec. So g little delta is, well, sub delta, whatever, is going to be g of x plus g prime of x times delta g. And so really this is just a kind of a linear approximation. If we had some function here, then in order to approximate it around this point, we want to have a constant in there that sets us up that many units to begin with, and then this is just going to be the line whose slope is the derivative of the function at that point. So we can do the same with h. So h little delta is going to be h of x plus h prime, h is in terms of y, so h of y plus h prime of y delta h. So let's solve these. G sub delta is going to be g of x, where x is 1, so g of 1 is 2, as they say, plus g prime of 1, which is 3, times our delta g. Well, we went from 1 to 1.1, so that's going to be 0.1. Then h delta is going to be h of y, for y is equal to 2, h of 2 is going to be 5, like they say right here, plus -1 times 0.2. So this works out to 2.3 and 4.8. And we know that f of xy is just these two multiplied together. So our approximation for f is going to be our that's not a delta. Our approximation for g multiplied by our approximation for h. And so 2.3 times 4.8, that's going to give us 11.04, which according to this exam rounds up to 11.1. Okay, the number of absolute maxima, the value, oh God, I can't read today. The number and value of the absolute maxima of this function on this domain is what? So Lagrange multiplier time, we know that fx is equal to, if we're calling this constraint function, g of xy. Fx is going to equal g of x lambda, and f of y is going to equal g of y lambda, where lambda is just some constant that makes these guys parallel. So fx is going to be 2x minus y, and that's equal to 4x lambda, whereas fy is going to be 2y minus x, and that's equal to 4y lambda. So now let's divide out some things. We will get lambda is equal to 2x minus y over 4x, and lambda is equal to 2y minus x over 4y. We can set these equal to each other. 2x minus y over 4x is equal to 2y minus x over 4y. We will, okay, let's multiply everything out. This is equal to 8xy minus 4y squared, which is equal to 8xy minus 4x squared. So our xy's cancel out, and we are left with -4y squared is -4x squared, or this simplifies all down to y equals x. Hello, I was going pretty insane there for a second. I I recorded the next couple questions, and then out of the blue, I don't know, the recording stopped and disappeared, and I never got it, and so that material is gone. So I'm just going to show you what we did for, I think, question 7. Oh no, great! I erased question 8. Not sure I'm doing that. Okay, we're just gonna, all this is gone. Goodbye. Oh God. So question 7, how we finished this one up. We found that y was equal to x, and we plugged that back into our g of x to find that x and y are both plus or minus -1/2. And then we took all those values and plugged them into our f of x over here to see how many of them were maxima. We found that 2 of them were maxima, but we also have to use the fact that this is less than or equal to 1. So this is actually a solid disk right here. So we had to use the second derivative test to look at the center of this disk, and we did that by making this matrix that we know that we have to use, and it turns out that matrix is just made out of constants. Oh no, I don't want to erase them. Oops. Made out of constants like that. And knowing this, we can see that no matter what, this determinant is going to be positive, and because the determinant is positive and f(x) is greater than 0, any critical points will be local minima, and so they do not count towards our count of local maxima, and we are done. Let's compute the double integral over the region R of cosine x plus y dA, where 0 is less than or equal to x, which is less than or equal to pi, and 0 is less than or equal to y, which is less than or equal to pi. So the double integral from 0 to pi, cosine x plus y dx dy. This is going to be sine x plus y on 0 to pi, and this works out to sine pi plus y. That looks exactly like an m. It's not an m, it's my crappy pi, and this will be sine y. So now we're left with the integral from 0 to pi of sine pi plus y minus sine y dy, which will work out to cosine of y minus cosine of pi plus y on 0 to pi, and this is going to work out to cosine of pi minus cosine of 2 pi, so negative 1 minus 1, and then cosine of 0 minus cosine of pi is just going to be 1 plus 1. So overall, we get negative 4. Okay, question 9, we are taking this weird, very, very weird rectangular integral. So we can set up our triple integral bounds with yz, I don't know, let's do dz, dy, dx. And let's check out our bounds on z. Well, z is bounded by z equals 0 and z equals y, so we can use that. So 0, y. What about y? Well, y is bounded by y equals x, and since y is equal to z and z is equal to 0, y is bounded on the bottom by 0. So there we go. And then x, the train gets even bigger because we see x is bounded on top by 1, but let's see, what about the bottom? Well, x is equal to y is equal to z, and z is equal to 0. So it's bounded on the bottom by 0. So now we can take our integral. So now that we have everything set up, we are ready to integrate. This is our first integral is going to work out to y z squared over 2 on 0 to y. This will be y cubed over 2, and that will be 0. So now we're taking the integral from 0 to x of y cubed over 2 dy. This is y to the fourth over 8 from 0 to x, and this is x to the fourth over 8. Now we're taking our final integral from 0 to 1 of x to the fourth. That looks like a 9, x to the fourth over 8 dx, which is x to the fifth over 40, evaluated on 0 to 1, which is just 1/40th. Thank God. Okay, the density of the solid sphere at any point, is proportional to the point's distance from the center of the sphere. What is the ratio of the mass of the sphere of radius 1 to sphere of radius 2? So figuring out what this density function is can be a pain if you kind of don't step back from it a little bit and think in a little bit of a weird way, because we need a measure that tells us how far we are from the center of a sphere in spherical coordinates, and there's one letter for it, and that letter is rho. So really, the density function is just rho, because rho increases proportionally to the point's distance from the center of the sphere. So we're taking two integrals here, and really it's a fraction. So we're looking for the ratio of the triple integral of rho, well, it'll be rho cubed sine phi d rho d phi d theta, and we want the entire sphere, so our bounds are going to be 0 to 1, 0 to pi, and 0 to pi, and 0 to 2 pi up there, and then we want the ratio of that over a sphere of radius 2. So this will be rho cubed sine phi, and of course it's rho cubed in here because it would be rho squared, but then we have to add in our rho, which is our density function. So d rho d phi d theta from 0 to 2 this time, from 0 to pi, from 0 to 2 pi. Well, this theta integral doesn't matter at all. We're not dependent on theta, and they will just cancel each other out, so we can get rid of that. And also, whatever this sine ends up evaluating to doesn't matter at all, because it will get canceled out by the other one that is exactly the same. So all we are left with is these two integrals, and this is going to be rho to the fourth over 4 on 0 to 1, which works out to 1/4, and this guy is going to work out to rho to the fourth over 4 on 0 to 2, which is 16 over 4, which is 4, and 1/4 over 4 is 1/16, and we're done. Let's find the area of the portion of this plane that lies in the first. Oh, great. Craig Miller's running late. I gotta. That is one notification I'll leave in. It's kind of funny. Okay, so we're looking for the area of this guy. We know that if we can express this in the form z equals something, that our integrand is going to be zx squared plus zy squared plus 1. So let's figure that out. 2z is going to be equal to 2 minus x minus 2y, and so z is going to be this over 2, which we can express in a little easier to read way as 1 minus x over 2 minus y. So now we can find our zx and zy. Zx is going to be negative 1/2, where zy is going to be negative 1. So this whole thing is going to be the square root of 1/4 plus 1 plus 1, which is going to be 9 over 4, which works out to 3 over 2. So 3 over 2 is our integrand, and now we need to take an integral over the xy projection of this plane here. So in order to do that, we're just going to set z equal to 0 to find our bounds. So we're going to have 3 over 2 integrated dy dx, because why not? We can do it whichever way we want. And the equation that we're working with is x plus 2y equals 2. So y equals 1 minus x over 2. So we can slap that in here as our upper bound on y, 0 to 1 minus x over 2, whereas our upper bound on x is just going to be this for y equals 0, which is 0 to 2. So now, make a little more space, cleaning out pretty much everything else. We can, oh no, I cleared out one of the bounds, that's too bad. We should be able to integrate and get our answer. So we have no y's in here, so this dy is just going to multiply our 1 minus x over 2 in. So this will be 3/2 minus 3x over 4, integral from 0 to 2 dx for our last step. That will be 3x over 2 minus 3x squared over 8 on 0 to 2, which will give us 6 over 2 minus 12 over 8. And let's figure that out. This is going to be 3 minus 3 over 2, which will just give us 3 over 2. Okay, question 12. This is a fundamental theorem of line integrals question. If you ever see one that's like this, where we have to do 1, 2, 3, 4 different parametrizations to do f dot dr, it is very likely that you can use the fundamental theorem of line integrals. But let's make sure. We know that the fundamental theorem of line integrals states that if our force function, our force field, our vector field f is the gradient of some potential function f, then we can evaluate f on our start values and our end values for x, y, and z in order to solve for this. And that's because if we're in a conservative vector field, this path that we took down here is going to have the same work done on it by the field as any other path to go to this point here. So it's path independent. All it cares about is the points that you start and end at. So to make sure that this is a conservative vector field, we have to take our antiderivatives of these guys and make sure that there aren't any discrepancies. So our antiderivative of this thing with respect to x is going to be y, y e to the x. Our antiderivative of this with respect to y is going to be y e to the x, and our antiderivative of this with respect to z is going to be z squared. So we see that we have overlap here. We only count our overlap once, so our function f, our potential function, is going to be y e to the x plus z squared. And there are more official ways of finding this potential function, and I urge you, if my method, makes sense in my head, and I feel like I can identify, conservative vector fields just fine with it, but it's hard for me to articulate what exactly is going on, and I know that in the syllabus there are real other methods. This is just the one that I use because I'm stubborn. So we have our potential function, and we see that we're starting at 0, 0, 2 and ending at 0, 0, 3, 0. So really we're evaluating y e to the x plus z squared on our end value, which is 0, 3, 0, and we are subtracting from that our potential function evaluated on our start value, which is 0, 0, 2. This is going to be 4. This is going to be 3. And so our answer is 1. Let's just make sure. Oh, sorry. No, our answer is not 1, and I can't do basic math at this point in the day. So, well, it is only 2:40 p.m., but I've been doing math all day. So, 3 minus 4 is -1. There we go. Okay, 13. Let's suppose that f of x and y is p of x and y I plus q of x and y j, and that the partial derivative of q with respect to x minus the partial derivative of p with respect to y is 2. So this is heavily hinting that we should be using Green's theorem. Green's theorem, if we remember, we can write that as the integral of c of f dot dr as being, not f dot dr, of p dx plus q dy. This is the same thing as the double integral over the area R, over the region R, of the partial derivative of q with respect to x minus the partial derivative of p with respect to y dA. And so they're being really cool because they're giving us this whole integrand here. So all we have left to solve for is the double integral over R of 2 dA. And we can also just, oh no, there we go, 2 dA. So all we have to do here is figure out how we're going to integrate over this path. Well, this is just a circle of radius 3 that is, we're tracing it out counterclockwise, and we're going one full time around because t is between 0 and 2, so we can do this in polar coordinates. And in fact, we don't actually have to do any calculus because we know the expression for the area of a circle is just pi r squared, and we know our radius is 3, so we're going to get 9 pi out of this, and we're multiplying this area by 2, so 18 pi is our answer. Okay, this question is a pain, but we have to do it. Well, I have to do it. You don't have to do it. You can skip this question, and you'll probably be okay. We're taking the divergence of f and taking the gradient of that, and then we're subtracting the curl of the curl. So let's figure this stuff out. We know, that the divergence is going to be del dot f. So we can set that up as partial x, partial y, partial z, all dotted with x squared yz, xy squared z, and xy z squared. And we see that we are going to get 2xyz, whoopsies, 2xyz plus 2xyz. I keep saying z and putting a square. I'm not sure what's going on. 2xyz plus 2xyz. So 6xyz is what we need to take the gradient of. And we see that that is, so gradient of this guy is just going to be the vector 6yz, comma 6xz, comma 6xy. Okay, we're halfway done, but not really, because curl takes a little bit longer. And we're just going to reuse this from right here. So we know that the curl is not del dot f, but del cross f is curl of f. And so pretty much we just have to do this twice, which is a real joy, you know? So we are going to get x, oops, I need to mark this, xz squared minus xy squared, comma, xy squared minus yz squared, and finally zy squared minus zx squared. And then we have to take the curl of this again. So we're going to get this guy out of here. We'll just stick him up here and make it really small, because why not? And move this thing up here. And I can't really tell where any of these begin and end, so I'm going to put big lines in between them. Okay, time for some more curl. We see that our first component of the curl is going to be 2zy minus negative 2zy. So this is good news, because we see that every component in any of our answer choices have the same coefficients. So because we know that this first component works out to 4zy, we can subtract that from our 6cy, like they tell us to do here, and 2zy, I'm relatively sure, thank God, is our answer. Okay, if surface S is parametrized by r of uv, then the equation of the plane tangent to S at 1, 2, 4 is what? Well, we know that RU cross RV is going to be our normal vector. So we can find that. These are just our partial derivatives with respect to u and v. RU is going to be 1, 0, v squared, and RV is going to be 0, 1, 2uv. So just to save you guys the pain and, well, both of us the pain, I draw my u's and v's very similarly, and so we're just going to go plug in these values right now. So RU is going to be 1, 0, v squared, which is 4, and RV is going to be 0, 0, 1, 2 UV, so also 4. So now we take a cross product, and we will have our normal vector. So crossing, we will get negative 4, and 1. So that's perfect, because now we can set up the equation of our plane, which we know to be defined by the unit vector, sorry, by the normal vector. So we have negative 4x minus 4y plus z, and that's equal to something. And we can figure out what that something is by plugging in 1, 2, and 4 for x, y, and z. So we will get negative 4 minus 8 plus 4 is negative 8. So we just stick a negative 8 up here, and notice that if we move everything to the other side of the equation, we will get answer choice E, which is equivalent to this. Let's let S be the portion of the surface z equals xy that lies within this cylinder, and we need to find the surface integral with z plus 1 in here. So we know that when we have something, a surface in the form z equals, we need, for these surface integrals, we need the square root of zx squared plus zy squared plus 1. We can find those really easily. Zx is going to be y, zy is going to be x, and 1 is going to be 1, like usual. So we have x squared plus y squared plus 1 in here. And since it's going to be a double integral over the xy projection of this surface within the cylinder, we need to replace this z because we only want to really deal with the x and y planes. But this is fine because we know that z is equal to xy. So we can replace this with xy plus 1. Perfect. So now all we have to do is all we have to do is put this into polar coordinates and take our integral. So we know that this is on the xy plane, this is a circle of radius root 3. So we can set up our overall integral as a double integral from 0 to root 3 on r and 0 to 2 pi on theta of, let's see, r squared sine theta cosine theta plus 1, all multiplied by root r squared plus 1, and then everything is multiplied by r, and then dr d theta. So this looks like an absolutely terrible thing to have to integrate, and to be honest, it kind of is. So we'll see what we can do. We can distribute our r into here and split this up into two different integrals. We're going to have the integral from 0 to root 3, 0 to 2 pi of r cubed sine theta cosine theta, all multiplied by root r squared plus 1 dr d theta. And then we are going to have the integral from 0 to root 3 and from 0 to 2 pi of r root r squared plus 1 dr d theta. And these guys added together, you can see how we've just split it up over that plus sign. Okay, so we're actually saved a little bit by the fact that just this small portion of the integral here that's multiplied into everything else, if we take this integral from 0 to 2 pi of sine theta cosine theta d theta, we will see that this is equivalent to the integral from 0 to 2 pi of 1/2 sine 2 theta d theta, which is 1/4 cosine, negative 1/4 cosine 2 theta on 0 to 2 pi. This is going to give us negative 1/4 and negative 1/4, which is 0. So it's very, 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 very nice that it works out this way. This whole integral is 0. So all we have to worry about, in fact, I'm going to delete the whole thing because I don't really want to look at it anymore. all we have to worry about is this oh no, that's not what I meant to do. So all we have to worry about is this integral down here. There we go. So we can do some u substitution on this and then reverse it again, and we will get the integral from 0 to 2 pi d theta of the quantity 1/3 r squared plus 1 to the 3 halves evaluated on 0 to root 3. And inside here, this is going to work out to be, let's see, d theta. This is going to be 4 to the 3 halves, which is root 64, so 8 over 3. And this is going to be 1 to the 3 halves times 1/3, which is just 1/3. So 7/3 it is. And then if we integrate 7/3 from 0 to 2 pi d theta, we will get 14 pi thirds. And that is our answer. I hate this question. Moving on. Let's consider this curve from 0 is less than or equal to t is less than or equal to 2 pi. And it's the intersection of this cylinder with this plane. They're being very nice to us in giving us this parametrization. So this is going to be a case where Stokes' theorem comes in handy, because we know that the integral over c of f dot dr is the same thing as the double integral over the double integral over s of curl of f dot n ds, which ends up being much easier because, as you'll see, when we curl our f here, all of this nasty trigonometric stuff is going to disappear into thin air. So speaking of curling our f, let's do that. We know that curl is del cross f, so that's going to be d dx partial y del z. I'm just mixing it all up now and saying all three of them. Isn't that crazy? So y plus sine x, z plus sine y, and x plus cosine z right there. So taking this curl, we are going to get -1, -1, -1. So there's our curl f. Now we need to dot it with our normal vector. Well, our normal vector, we're looking at our surface here is just a plane intersecting a cylinder. So the normal vector is going to be whatever the normal vector of that plane is, which in our case is just 1, 1, 1. So sticking 1, 1, 1. And here this dot product is going to be -3. And since this integral over s of -3 ds, all that's going to be doing is multiplying -3 by the xy projection. So this surface, if you were to, like shine a light up here, whatever shape this makes on the xy plane would be what we are essentially multiplying -3 by. So in this case, it's just going to be the outline of the cylinder. Our cylinder is of radius 1, and so our area is going to be pi. So multiplying pi by -3, we get our -3 pi. 18, we have to find the flux of this function, this force function f. It's not necessarily force, it's just our vector field f out of the box with 6 faces, where 0 is less than or equal to x, which is less than or equal to 1, 0 is less than or equal to y, which is less than or equal to 2, and 0 is less than or equal to z, which is less than or equal to 3. And those will be useful for our integral later. We know that we can use the divergence theorem for this because we're in a closed box and we're looking for flux. And so this is going to be equal to the divergence over, I don't know, let's call our box B, B for box, over the region box of the divergence of f dv. So in order to find that, we have to find our divergence of f. Well, our divergence of f is just going to be del dot f which in our case is going to work out to 0 because z squared dx is going to be 0. This guy dy is going to be x, and this guy dz is going to be nothing. So divergence of f, let's actually write this out. Z squared partial x, xy partial y, and y squared partial z. So as we said, this dot is 0, this dot is going to be x, and this dot is also 0. So divergence of f is x, and we're left with the integral over this region, which we know can be expressed with dx, dy, dz, where x runs from 0 to 1, y runs from 0 to 2, and z runs from 0 to 3, and our integrand is just x. X squared over 2 on 0 to 1 is 1/2, and since we don't have a y or a z in here, all we have to do is multiply by these guys. So 6 times 1/2 is going to give us 3, which is our answer. Okay, this one's kind of a killer. So question 19, let S be the upper hemisphere, x squared plus y squared plus z squared equals 4, with the normal vector pointing towards the origin, and F is z times the radial vector field x over magnitude of x, where x is x, y, z, which is, they're just putting it in another form for us. And we are looking for the flux integral here. Okay, so this is a daunting one. Let's write out all of our components of f. So f is equal to xz over root x squared plus y squared plus z squared, comma, yz over root x squared plus y squared plus z squared, and z squared over root x squared plus y squared plus z squared. There we go. Okay, so we know that we can work through this problem by finding the normal vector to this upper hemisphere, finding the normal vector that they want, and doing the double integral over s of f dot n ds. So let's find that normal vector. Well, the normal vector to an upper hemisphere, that's not looking too good, but we can express this in the form of z equals. So we can take this thing and say z equals root 4 minus x squared minus y squared, which will be very useful very quick, because we know that we can express our normal vector in the form of zx, zy, -1, because we want our normal vector pointing towards the origin. So let's find zx and zy and take our dot product, and so many things will cancel and it'll be very satisfying. So make sure to stick around. Zx is going to be -x over root 4 minus x squared minus y squared, and zy is going to be -y over root 4 minus x squared minus y squared. So we are taking, let's move this out of the way. We are taking this f dotted with this guy, comma, this guy, comma, -1. And when we take this dot product, we'll notice that we still have z's left over in here in our f. We have a z, and a z squared. So we actually do want to get rid of those. And we know that z is equal to root 4 minus x squared minus y squared. So we can substitute that in. Root 4 minus x squared minus y squared. Root 4 minus x squared minus y squared. And this will just be 4 minus x squared minus y squared. So now we'll also notice that we have z's stuck down here. We have z squared stuck down here. And we just found z squared, that z squared is 4 minus x squared minus y squared. So we can replace the z squared with 4 minus x squared minus y squared. And these denominators will just turn into root 4, which is just 2. So already some magic is starting to happen. There we go. And then we'll see as we take this dot product that this root 4 minus x squared minus y, oh, whoops, that's the eraser. This root 4 minus x squared minus y squared is going to cancel with this one, and this one's going to cancel with this one. So we can get rid of that and that, and that and that. And so now we have a much easier integral to deal with. This is going to be negative x squared minus y, negative x squared over 2 minus y squared over 2 plus, there we go, minus 4 plus x squared over 2. Oh, God, my math is not doing too good today. This is going to be minus 2 plus x squared over 2 plus y squared over 2, which leaves us with negative 2, and all we have to do, here we go, negative 2, is multiply by the xy plane projection of the kind of the shadow of this upper hemisphere, which because it's a circle of radius 2, will give us, a equals pi r squared. That's going to give us 4 pi. Multiply by negative 2, we get negative 8 pi. 19, our answer is A. That's the first. That was take one, and I bet it was mostly unintelligible because there are still things. This question, I don't necessarily have it all down yet, but hopefully that was a little helpful. God, but I hope you see how all of everything canceling out is very satisfying in the end. Okay, finally, we're out of here. Let's consider this radial vector field where x denotes, that radial vector. Which of the following is true? So we have a little rule that's going to help us. The divergence of f, if f is a radial vector field in this kind of form of f equals x over magnitude of x to the p, we know that the divergence of f is 3 minus p over magnitude of x to the p. And this is great for us because this tells us that on our maximal domain of definition, the divergence of f is 0, because in our case, p is 3. Okay, moving on. Let's see, curl of f is 0 on its maximal domain of definition. Well, we're dealing with a purely radial vector field, so this is, for every point, this is just in the xy plane, but you'll see what I mean. For every point, it is its tail is going to be pointed directly back at the origin. And so hopefully you can see how, doesn't matter what size of surface we kind of put around this, there is no curling anywhere happening. There's a point source in here and nothing working to swirl things around otherwise. So our curl will be 0 on our maximal domain of definition, and I'm not sure why they bolded this 0 here. Yeah. Okay, so then all they're doing here is trying to get you to recognize this is an integral for curl, and this is an integral for flux. And they're saying, excuse me, for any closed surface on which f is defined, that our flux is equal to 0. Well, we just saw that there's a lot of flux going around here. If we were to put a sphere around this point source, uh, because it's a source, there necessarily have to be, you know, vector lines flowing out from that source, out of whatever we put around it. So this is going to be false. And let's see, 4. Well, we already agreed that there are no curling influences on this vector field because it's purely a radial vector field. So taking an integral for curl or circulation or whatever, we will always get 0. So 2 and 4 are our answers. And okay, we are done. Please let me know if any of this was confusing. I'm sure most of it was. And thanks for making it.